There are some cases where specificity is of high priority. Not every time sensitivity is of high priority. There are some class of problems where specificity need to be really spot on. It need to be 100%. We just can't compromise on the specificity. So one such example is testing or predicting whether a medicine is good or poisonous. Let us suppose 0 is good, yes the medicine is good, and 1 is yes the medicine is poisonous. Now those are actual values, and we are building the model, or we built the model, and the model is predicting them as good or bad, which is poisonous. When the actual value of the medicine, when the actually medicine is good, our model is predicting is good, that's fine. When it is actually good, our model is predicting poisonous, then what we do is we throw away the medicine. When it is poisonous, predicting it as good and consuming it, using it, is really problematic. So false positives here are really dangerous. A false positive value can cause a real big issue in these type of values. So here a simple false positive is not equal to false negative. When we have a false negative, we ban the usage. Even the medicine is good, we ban the usage. Whereas when the medicine is really poisonous, when our model predict it as good, then we recommend it for usage. Now that is really dangerous. So that is the case. This is a different problem where specificity is really important. So we want to maximize the specificity here. We will be very careful to maximize the specificity. We want to have, whenever it is poisonous, we want to predict is absolutely poisonous. So that is the case where specificity is really important. So while testing, in fact this might look very similar to the opposite of the problem where sensitivity is high. So there are certain class of problems where first class, that is yes or good value or is really important. There are certain classes where the no value or the poisonous, here in this case, is really important. So there are some classes where sensitivity is important. There are some classes of problems where specificity is really important. Okay, in this case definitely we want to avoid the cases like the actual medicine is poisonous and the model is predicting good, that is false positives. We just want to completely avoid them, and we want to have the specificity near to 100. Okay, so these are certain class of problems where sensitivity is not at all a problem. It's the specificity that we want to maximize. One more model validation technique is ROC curve. It is again related or connected to specificity and sensitivity. What is ROC curve? If we consider that all possible threshold values, and whenever we change the threshold value, the sensitivity and specificity, both of them change. So what will be the actual final accuracy? Whenever we change the threshold, the specificity changes, the sensitivity changes, and then the model accuracy changes. But actually what is the true accuracy value? Okay, ROC curve is drawn by taking the false positive rate on the x-axis and sensitivity on the y-axis. Sensitivity is nothing but true positive rate on the y-axis. What exactly this false positive rate on x-axis and true positive rate on y-axis, why exactly it is taken? So false positives is nothing but mistakes that we are making while finding the positives, right? False positive, falsely classifying them as positives, and true positives is what, how many of them we are rightly classifying. When it is positive, we are rightly classifying as positive. So what exactly ROC tells us is how many mistakes that we are making, that is false positives, while finding the true positives. Let us suppose to find the 80% of the true positives. To find 80% of the true positives, let us suppose this point B, how many false positives I am finding, how many false positives, that is how many mistakes that I am making. To find 90% of the positives, how many mistakes, it's not 100, it's 90%. To find 90% of the positives, how many mistakes, that is false positives, that I am finding. 1 minus specificity is false positives, whereas specificity is true negatives. So how many false positives or how many mistakes that I'm making to find 100%? So obviously to find 100% positives, I'll make 100% false positives. So we have to make as less mistakes as possible to find the maximum positives. So to find all the true positives, we want to make actually 0 errors. We don't want to classify anything as false positives, but obviously our model will be having some error. We want to have least error, least positive false positive rate to find the maximum true positive rate. So ROC curve, at all threshold, at all sensitivity and specificity values, it will draw the false positives against the true positives for all the models, and we will be able to see what are the number of false positives that we are making given how many true positives that are found. And ideally, for a good model, we want this area under the curve. We want to make actually for only very few false positive errors, we want to find out 100% actual 100% true positives. So for these many false positives, we want to find 100% of the true positives. So that is, we want this area under the curve to be really high for a good model. So an indication of good model is for ROC, the area under the curve need to be really high. Now that comes with a connected topic called area under the curve. Just ROC standalone, yes, we can interpret the ROC, but quantifying the real impact of the model or the real accuracy of the model, we have to look at the area under the curve of the ROC curve. So it is ROC and AUC, area under the curve of the ROC curve, area under the ROC curve. So the area under the ROC curve need to be as close to 1 as possible. For a good model, it really indicates that area under the curve is really high, which means that we are making very few errors. We are making very few errors given to identify 100% of the positives. So for a good model, the curve will be as far away from this random line as possible, and this area under the curve, this whole curve till here, it will be near to 1. For a bad model, area under the curve will not be near to 1. So ROC curve gives us the overall performance of the model, whereas area under the curve tells us, quantifies the exact value, looking at which we can directly tell whether the model is good or bad. So area under the curve, if it is 1, the model is really good, perfect model. If it is 0.82, yes, it is nearly good. If it is 0, then a model is not at all useful. So we want the area under the curve to be more than 85%, depending on the data and other conditions. So for a good model, as near to 1 as possible is our criteria. Area under the curve need to be near to 1. Once again, what exactly area under the curve? That is, first of all, area under the curve comes from ROC, and ROC is created by taking, it is simply the average number of mistakes that we are making while predicting the actual true positives. So the true accuracy when compared it with our error is the ROC curve, and area under the ROC curve is need to be near to 1 for a good model. Now let us see how to calculate ROC and AUC, area under the curve. So we'll consider the data set, product sales data, simple data that we used in logistic regression, in that there are two variables, age versus buying a product or not. So we predict based on age whether a person will buy the product or not. So we built a logistic regression model for the same. So we have a logistic regression model. Now we already have the accuracy and confusion matrix. What we want to see is the overall area under the curve and ROC curve. So in fact, if we want, we can actually again do the confusion matrix, but anyway we will skip that. Now we will directly go ahead with the ROC curve. For ROC curve we need the predicted probabilities. So these are the predicted probabilities. We have the actual predicted probabilities. Now the input of ROC curve is predicted probabilities versus the actual values, the actual model values, that is y, that is buying. So we store that. We need to use ROC function. Now ROC function is in a library called PROC. So PROC library need to be installed. So it attaches few other libraries. Now using PROC, now we can run the ROC function. Now ROC is created, we just need to now plot ROC. Now this is the ROC. As we discussed, this ROC curve need to be as much away from the actual line as possible. Area under the curve is already given as 98.3%. in fact, we have directly AUC function, area under the curve is 90.908, or we can even write it directly without ROC curve, predicted versus actual, or actual versus predicted. We can get the area under the curve. Now let's do this for a different model, slightly complicated model, that is fiber bits data. Now this area under the curve and ROC are calculated at every level of sensitivity and every level of specificity. So how many mistakes on an average we are doing at for every model if we build multiple models. So it will take some time definitely to calculate area under the curve. So let us do that on a bigger data set, fiber bits model. First we are finding the predicted probabilities for fiber bits model. So these are the predicted probabilities for the fiber bits model, and then ROC curve. First we'll use ROC function and store it in the ROC curve. As we discussed earlier, it will take some time to actually create the ROC curve. Once it is created, we can plot it quite quickly. It's still taking some time, still executing. Still executing. So ROC will be considered at every threshold value, what is sensitivity, what is specificity. When threshold is 0.1, 0.2, 0.3, 0.4, so there are so many permutations and combinations that a threshold will go through and find the values of predicted probabilities and specificity and sensitivity values, and finally store them in ROC curve. And then once this is done, we can save it in ROC and see the AUC curve. This is old area under the curve. I just stopped the process.